So today we're talking about the use of statistics to improve the integrity of research data. Yeah. Now, any statisticians in the room? There's one at the. You're a statistician. When do you usually get involved in research? Do you do your own research in biostatistics? But when others ask for your help, when do they come to you for help? Yeah.
Or after collecting data.
Yeah.
So sometimes coming.
Okay. So there are two times that you're mainly involved in research. That means at the very beginning, when they say, usually it's a sample size estimate, isn't it? And the answer is always 100, isn't it? You know, they tell you, I've got 100 patients. What's my sample? You know, can you make my sample size estimate? And so you have to make a big effect. So it comes. So usually statisticians are involved at the very beginning, and to help with sample size estimations, and at the very end to help analyze the data. But what I'm going to make the case for is actually the important but neglected role of statisticians in the middle, yeah, during data collection. I think that's a really important place for statistics to be involved, and that can improve the quality of the data. Yeah? So it's about using statistical methods to check the validity or the accuracy of the data as you're going along in a study. Yeah? So I told you about this study that I'm going to start from the beginning about the way you can use statistics to help check the data integrity. So in 2009, I mentioned this paper the other day. In 2009, we wrote this systematic review of tranexamic acid in postpartum hemorrhage. And we found all of these trials, and we concluded, and we believed everything that was written on the paper, and we believed that tranexamic acid reduces blood loss. And then, but since then, we've become more skeptical. Now, we talked about this, about the most important. This is a randomized trial, very simple structure, and we talked about the key element of a randomized trial is this. It's the randomization and allocation concealment. And I think it was Tomoko who said that the key word is unpredictable. Was it you? Yeah. So that's the most important thing. The allocation must be unpredictable. Yeah. So that's really important. So if the allocation is unpredictable, then chance and chance alone determines who gets into these two groups. Yeah? And so these two groups should differ only by the play of chance. Yeah? There shouldn't be any differences. There can be differences, but they're chance differences. But there shouldn't be differences over and above the play of chance. Now, we do, I love randomization because of its fantastic ability to balance baseline variables. So in this big trial we did of tranexamic acid for the treatment of traumatic hemorrhage, you know, this woman's been shot or stabbed in the stomach, and so she's been randomly allocated to tranexamic acid or not. And this is the first table in any research paper of a randomized trial. It's the baseline comparisons. So it's comparing those who got the treatment and those who didn't get the treatment, so the drug and the placebo group, before they've received the treatment. Yeah? So you collect the information, you've randomly allocated them, and you're just looking at the baseline variables. Yeah? And it's fantastic. You know, it's beautiful, I think. they're so beautifully balanced, you know. All of these factors, I don't know if you can see it from over there, it's quite difficult to see. But all of these things are, you know, really well balanced, you know. 15.5% had a low blood pressure, 15.9% in the placebo group. Really, you know, so you get a really nice balance. So randomization, when it's done correctly, is really beautiful. So if you do proper randomization, you'll get two groups that differ only by chance, yeah? And who is talking about doing meta-analyses of studies and finding out that they weren't, you did a meta-analysis of studies and then you found that the studies weren't, wasn't, yeah, so what really happened wasn't mentioned in the paper. Is that what you found? Tell us what you found.
Was not written in the paper.
Yeah.
They wrote that they did a randomized control trial.
Ah, that's it. Yeah, they used the word randomized controlled trial, but they hadn't really randomized. They were either confused or...
Actually,
It was intentional, okay.
otherwise the paper wouldn't be published.
Ah, I see. Okay. All right. So, this is a good trick that you can do to see if studies are really randomized or not, right? So, if they're really randomized, then the two treatment groups should differ only by chance. And if you do a meta-analysis of the baseline variables, yeah? Now, usually we do a meta-analysis of the outcome variables, don't we? So, you know, you want to know if this treatment has an effect. So you do a randomized trial, you randomize this, patients get this treatment or that treatment, you follow them along, you get the outcomes in the two groups, and you do a meta-analysis of the outcomes to see what effect the treatment had. Well, now we're doing something different. We're actually doing a meta-analysis of the baseline variables, yeah? And we shouldn't see any average difference, should we? Yeah? And we shouldn't see any heterogeneity over and above chance, yeah? There shouldn't be any heterogeneity. Do you know what heterogeneity is, everybody? Heterogeneity is like sort of variability over and above chance, yeah? Callistus? Yeah? So you shouldn't see any overall difference and you shouldn't see any heterogeneity. So we went back to this meta-analysis we did of tranexamic acid in postpartum hemorrhage, and we did a meta-analysis this time of the baseline variables. We had done a meta-analysis of the outcome variables, but now we were actually wanting to learn, actually, were these really randomized trials? Let's do a meta-analysis of the baseline variables. So we took two key variables. Age is a good one. Age is a prognostic factor for lots of things, and it's used almost always age is one of the baseline factors. So you can do a meta-analysis of age. So we did a meta-analysis of age, and there was the patients in the treated group were significantly younger. That's a bit. So that shouldn't really happen. I mean, maybe it could happen really rarely by chance, but it shouldn't really happen. It makes you a little bit more suspicious. So there was a significantly lower, age was significantly lower in the treated group, and an important one considering the outcome is blood loss, the baseline hemoglobin, so that they're trying to see if tranexamic acid reduces blood loss, and they're measuring the difference in the baseline to the follow-up hemoglobin. And so the baseline hemoglobin was much lower in the treated group. I'm not sure what direction. Anyway, it should be the same, ideally, but it was different. And also, there was significant heterogeneity. these differed more than you'd expect by chance alone. So, so that's a bit strange. So that made us a little bit more suspicious. Now, this is new stuff. People recently have started using statistics like this. What you do is you take all of these trials and you work out a t-test. Yeah? Everybody familiar with a t-test? It's a t-test for the difference. It's a significant test for the difference in the baseline variables. The mean difference, the t-statistic, and the absolute value of the t-statistic. And then you rank the studies by the t-statistic. So you rank the study by the size of the difference between the groups. And then you you delete them one after another until you get zero heterogeneity. And then you do a meta-analysis of those studies and see what they show. Yeah? So it's like doing a sensitivity analysis. It's like saying, okay, if these studies are properly randomized, chance and chance alone should determine who goes into the both groups. We can get differences in the baseline variables, but they'd only be due to chance. And if you do a meta-analysis, you shouldn't see very big differences. But if you do see differences, then you can exclude the studies based on the size of the differences and then do the meta-analysis again and see what effect it has on the results of the meta-analysis. Is that clear? It's a bit complicated, isn't it? What do you think? Tomoko, in your meta-analysis, tell us about your meta-analysis. What were you doing?
It was about to assess the effect of kind of
Extracorporeal.
circuit for a severe critical ill patient.
Yes.
And there were 12 studies
Uh-huh.
conducted, and 6 of them were from the same point group. And those 6 studies were very small.
Yes.
Small sample sizes, and their description in papers were very ambiguous, and I cannot find out what they have done clearly from the paper. So I asked them what they have done
Yeah.
in their studies, and found that they have not done randomization,
Yeah.
but they wrote intentionally that they have done randomized control trial.
Yeah.
He said that it's because of the paper to be published
Ah.
in the journal.
Well, you had a very honest.
But they didn't answer to my email.
Yeah.
They didn't write.
Oh, it was when you called them, wasn't it? And these were researchers in Japan. Okay. And you called them and they said, oh, it's because it wouldn't get published otherwise. Okay. And what did you do afterwards? Did you do anything?
I excluded from my analysis because it is not a randomized control trial
Hmm.
for my research.
Yeah.
And because after I wrote that, actually it's not published yet, so I cannot say everything I wrote. I excluded 6 studies from this analysis because we found that was not a randomized control trial after the inquiry analysis.
Yeah. Okay.
Yes, that's.
And you'll leave it there.
I don't know because it's ongoing. Meta-analysis is ongoing.
Hmm.
And my paper is not published yet, so I don't know what the reviewers will say about that, or scientific community,
Yeah.
our community, our scientific
Yeah.
community will say about that, because
Ooh, it's an interesting one, isn't it?
yes,
Who think?
it's a little bit scary.
What do you think Tomoko should do? Has she done enough? Now she's identified these studies as not being randomized, and she knows that they were said to be randomized so that they could be published. And it was intentional. So it puts you in a difficult position now, doesn't it? I mean, in a way, I mean, it's difficult or easy depending on how you want to do it. You can say, well, okay. But what do people think? What's her responsibility? Or does she have a responsibility here? What do you think?
I don't understand. Because she wants to, she can try, because she like to explore that. I think she has the right for that as a researcher.
She has the right to expose it.
Yeah, if she wants.
Yeah. And what will happen to her if she does? Yeah. So was this a university?
The researchers'
Ye-
affiliation?
Yeah. I mean, they were local hospitals. Okay. Yeah.
I think it's dangerous for her.
You think what?
Yeah, I think it's dangerous
It's dangerous for her.
for her to write such words in the paper.
Yeah.
Since if other readers read this, and they would all think, oh, if anyone call me and ask me my trials, I will not be honest anymore.
Oh, I see.
Then also with the phone call there is no evidence. She cannot
Yeah.
provide any evidence. So
Actually,
the
a
all
phone
task
call,
are
if
just
you want to
case.
record the phone call, is an evidence.
Yeah, but maybe she did not give this. I don't know.
Yeah.
Without consent, right?
And you don't know what they're going to say in
Yes.
advance. I don't know they're going to say such thing. So
Because
why would I
even-
record all my
Even if you write like a letter to the editor, maybe,
Mm-hmm.
but you don't have you have nothing to cite for.
Yeah. I mean, I think what you've done is, I mean, most people would think that's reasonable. You know, you've put it in the paper that they, you know, you've investigated and you found they weren't properly randomized. It's a very difficult one, isn't it?
But the question would be in your manuscript, did you include reference to those studies that you didn't include? Because if you just say, I excluded a number of studies because they were not randomized, but me as a reader don't know which studies are these studies.
Of course.
Oh, you okay. Well, at least that's something. I mean, if I'm in the same area, your same research area, and I read your paper, I will check which ones were excluded because they were not randomized. At least it's something.
Maybe. I think other people will do a meta-analysis and they'll include them because most people take them at face value. So they're little bits of dangerous material in the literature. I mean, if they're not randomized trials and they're called randomized trials, then maybe they should be retracted? No? You don't think so? You disagree? They should be taken out of the literature, you know.
They should.
They should.
But some of my colleagues said that they were already academically retired, so
Ah.
not interested in.
Oh. Well, they might have retired, but the paper's still there. The paper won't be retired ever. The paper will be there for all time.
Another problem is those studies have already included in the previous systematic
Yeah.
reviews.
It's very difficult. It's very difficult. In fact, I think I told you about this one. So you know, these are the studies that we found in this meta-analysis, and we found out they had all of this same mistake, and then we looked at the papers, and they were all the same text, and then we found that they had the same results. And then we wrote this paper, does tranexamic acid, and we changed our previous conclusion. We said, in 2009, we said tranexamic acid reduces bleeding after postpartum hemorrhage. But this time, we decided to tell the truth. So we wrote this paper, and we said, there is no evidence that tranexamic acid reduces bleeding in postpartum hemorrhage. Most of the trials, a large proportion of the trials, are fraudulent. What happened? So we wrote that. We wrote our evidence. We showed that we showed the baseline variables. We'd written to the authors, asked them for the data. We'd checked the data, found it was wrong in many cases. We asked them about ethics committee approval, and then we checked with the ethics committee, and we found many cases where there was no ethics committee approval, and they said there was. And then we asked the authors, and they said, well, actually, no, you're right, we didn't get ethics committee approval. So, we had all of this, and so we said, let's just tell the truth, and let's just tell exactly what happened. So we wrote a paper saying exactly what happened, and we sent it to the Lancet. So what happened next?
More enemies.
What? Well, what did the Lancet decide to do?
I think it should normally publish the paper.
Yeah.
And also take steps to investigate if some of these papers were referenced to were published in the Lancet. Normally, it should take steps to retract them if the fraud is.
Oh, they weren't published in the Lancet. We wanted to publish a systematic review in the Lancet showing that previous research was fabricated, was fraudulent. So what would the Lancet say yes to this, or what would it say?
If you have evidence, I think we ought to say yes.
Really? So you're the editor of the Lancet, right?
If you have enough evidence to make
Oh.
them believe.
All right, let's do a role play. Right, Callistus, come and sit here. You're the editor of the Lancet. So Callistus is the editor of the Lancet. Who wants to be Callistus's Bengoshi? Yeah. So you could be Callistus's Bengoshi, right? And then we say, editor, here's a paper. It shows that these studies were fabricated, and we think they're fraudulent. We think it's important to tell the truth. What are you going to do?
Thank you for submitting your manuscript.
He's an expert lawyer. They all say that. Yes. Right. What's going through your head now? Now you're the editor of the Lancet. What's going through your head?
Unfortunately, we receive many papers.
Ah, yes. You must have been rejected many times. He knows all the words for the rejection. Unfortunately, we received so many papers.
Well, I think if I'm the editor, I'll share it with the editorial committee.
Yeah.
And make a decision. I think it's difficult to really decide.
Yeah. And what would your lawyer, what would you be saying to him? He's thinking about publishing a paper that claims that other research is fabricated.
I think it's the risk to engage in such a manuscript is that it can be very controversial and it can elicit a lot of reactions, and sometimes a journal doesn't want to be involved in such issues. They want to keep a good reputation and everything. So,
Well, I mean, what's the actual risk? I mean, I think you're talking now. you're the lawyer working for the Lancet, and the editor's thinking of publishing a paper. You're the lawyer. What are you worried about? What's the risk that you're worried about?
Worried about being sued, complaints from.
You're worried about being sued. Okay. So what do you say to the editor?
To avoid problems, to politely reject the paper.
Reject the paper.
Just in case we don't have all the evidence really showing that those research were fraudulent. So
Yeah.
I would suggest that we don't get involved in that.
You would suggest you don't get involved. Okay.
But I stand for telling the public the truth.
Yeah. So we've got Callistus, who has got a social value of wanting to tell the truth, but your lawyer is saying that this is putting your journal at risk, and maybe putting your job at risk. You know, if the Lancet gets sued, you might lose your job. So now you've got to weigh your responsibility to the truth against the possibility that the journal, under your, as a result of your decision, might get sued. What do you think?
I want to look at the evidence that the authors have.
You want to look at the evidence that the authors have. Okay.
Get advice from my lawyer whether this evidence can stand in law court.
Okay, so that's very sensible. He wants now to get advice from his lawyer about this manuscript. So this manuscript's become a very special manuscript now. It actually has to be legally defensible, yeah? And the lawyer is going to advise on this. And what sorts of things? You'll want evidence, won't you?
Yes, yes.
Yeah. Everything that's said in that manuscript, you'll want to see the evidence.
Not necessarily everything, but at least if I can have some documented proof where authors are recognizing that they have manipulated data, like in their case it was a call phone, but if it could have been written, that would be something good, because I have a document where they're showing that they did something
Yeah.
wrong, and
Well,
this can be exposed in the courts.
so what Tomoko says is that she rang up the authors and they said that they said it was randomized in order to get the paper published, but in fact it wasn't. Is that evidence?
On the personal note, yes, but in terms of the law, I wouldn't dare going with that, because it's going to be my word against theirs, and
It's going to be Tomoko's word against theirs. And when challenged, that you could pick up the phone and say, no, we never said that.
Yes.
I didn't say that at all. So it's getting more complicated, isn't it? Now, how do you make a living?
defending people.
You make a living defending people. So you're giving this advice to the Lancet. Are you giving it for free?
I'm being paid.
You're being paid. So the Lancet will have to pay you for your time to review this manuscript. And this manuscript's going to require a lot of work, isn't it?
Yeah.
And you're going to charge by the hour to the Lancet, aren't you?
For sure.
So it gets more difficult for Callistus now, because Callistus now has got to think, right, if I'm going to accept this paper, I have to pay legal fees to my lawyer to give me advice on it. I risk being sued by the angry researchers. I risk, there's a risk I could lose my job. What are you going to do?
This is just one of the 1,000 papers.
And this is just one of the 1,000 papers that come across your desk. See, Callistus made the right decision the first time from his point of view, didn't he? He says, unfortunately, we get a lot of papers and yours isn't, you know, despite being very interesting, we read it with great interest, you know. They just take one look of it and say, no way am I going to publish this, yeah? And that's what always happens. So journal editors, when they get a sense of any misconduct, they will always reject. If you're alleging misconduct in a journal article, thank you, Callistus, that was you did a good job. They will always reject, you know, because it's not in their interest to do anything otherwise. And so why does the public think that science is self-correcting? You know, the public thinks that if something is published and it's wrong, that actually other scientists will make that known and it will get corrected. That's the general view, isn't it? That's what scientists claim about research. You know, the good thing about peer-reviewed research is actually if something goes wrong, you know, other people will tell us about it and it will improve, yeah? But is it true? It's not true at all. It's completely the opposite. Everybody wants to hide it. You know, absolutely everybody. I've gone off statistical data monitoring, but this is, you know, but you won't. So we tried to. This paper, so the Lancet said they didn't want to publish the paper because, and they said, you know, we should take it up with the universities of the authors involved. So we did do that, and the universities, I wrote to all the universities of the authors, and they don't even write back. They don't even write back. So the universities, why would they write back? You know? So they go, oh yes, how interesting. One of our researchers, you're accusing one of our researchers of fraud. Oh, we'll look into this. No, they don't do that at all. They just ignore you, you know. And like I did, I went away because, you know, I haven't got time and money to investigate. It's not my job. So we found a journal that had published these papers without noticing their flaws, and it was an obstetrics journal. And I said to the editor, it was an editor I knew, and I said, you know, these are wrong. You know, the conclusions are unreliable. But they agreed to review the paper. It did go out to the lawyer, and the lawyer took all the strong words out of it. So we didn't say, you know, so it ended up existing trials are unreliable with serious flaws, you know. That's where we came to at the end, you know. So they take all of the anything controversial out of it. So it's I think it's a broken system, really. It doesn't work very well. Anyway, back to statistics. So this use of p-values is very interesting. So who can tell me what a p-value is? It's a kind of, it's quite often misunderstood, p-values. Does anyone want to have a go? Everybody's getting very nervous now because everybody feels they should be able to explain a p-value. When we interview staff in my unit, I ask them to explain a p-value. And you know, they have master's degrees and PhD degrees, and they can't do it. Anybody want to have a go? Do you want to have a go? P-value?
I use p-value when I want to compare two groups of more groups.
Yeah, that's what they're used for. But anybody can say what they are actually?
The first step is I null hypothesis.
Yes! Yes, that's it. Right, she's got it. I'll give you a job. Most people get that wrong. So you always start with a null hypothesis, right? So the null hypothesis, in a randomized trial, what's the usual null hypothesis?
The null hypothesis that there is the baseline, the two groups, they have no difference.
The null hypothesis that the treatment has no effect.
Oh,
Yeah? Yeah. So there's no effect of the treatment. So the outcomes, so if you randomize two people to get a drug, not to get a drug, and you follow them up and you see a difference, the null hypothesis is that the treatment has no effect. Yeah? So you've started in a really good place. You start with the null hypothesis. So whenever you see a p-value, that's the question you've got to ask. What's the null hypothesis? Yeah? And that helps you to understand the p-value. So the p-value then, see if you can keep on going. You're doing well so far.
First we put out the null hypothesis.
Yeah.
For example, the outcomes of two groups have no difference.
Yeah.
And then we the two groups have their outcomes have distributions, and we want to compare their mean distributions, have their distance is significant or not.
Yes. So first of all, you have a null hypothesis. The null hypothesis is that there's no real difference.
Yeah, no real difference, and the mean.
And then you've got some data.
Yeah, I got some data. Difference is about mean difference.
Mm.
The null hypothesis, the mean difference is a distribution of 0. But when we get the real data, the two groups, their mean difference may be distributed from the 0.
Yes. So you've got a null hypothesis of no difference. Then you get some data, and there's a bit of a difference.
Yes.
Yeah? And then the p-value is, if the null hypothesis is true, what's the probability that I would get results as large as a difference as large as this by chance alone, isn't it?
Yeah, by chance alone.
Yeah? So when you start off with this null hypothesis, and then you've got some data, and you're saying, if that's true, how likely is this data if that's true? And so if you've got a small difference, then it's quite likely. But if you've got a very large difference, it gets less and less likely. So the p-value is the probability that if the null hypothesis is true, that you'd get results as extreme as the ones you've got. Yeah? So if you have a p-value of 0.05, what proportion of results are compatible with chance alone?
5%.
5%. Yeah? Everybody agree with that? If the p-value is 0.05, then there's a 5% chance of getting a result as big as that just by chance. Now, if the p-value is 0.1, what's the probability of getting a result like that by chance alone? 10%. If it's 0.15, what is it? 15%. If it's 0.2, all right, you've got it. So the p-value should have a uniform distribution, yeah? So we've gone 0.5, 0.1. So, you should have the same chance of having a p-value of greater than 0.8. The same chance, you should have the same chance of getting a p-value of greater than 0.8 as getting a less than 0.2, yeah? Because the distribution is uniform, yeah? Do you get that? Everybody? Bit complicated? So the p-value should have a uniform distribution. Now that's been used very well. There's a very have you heard of Yoshihiro Sato? No? Mitate Hospital? Anyway, it's a kind of reasonably well-known, for people who are interested in misconduct, it's a reasonably well-known case of misconduct. It's a researcher in a hospital in Japan, and he researches on a drug to increase bone density, yeah? And these are, and he makes randomized trials, and somebody looked at the distribution of p-values in his randomized trials. The distribution of p-values for baseline variables, yeah? And this is the distribution of p-values for baseline variables. So what do you notice about that? So basically they looked at one variable, say age, and looked at the p-value, and then recorded it, and then, you know, and he had lots and lots of trials and lots of baseline variables, and this is the distribution of p-values for baseline variables. What does it show? What does it look like? Anybody? Well, I said that it should have a uniform distribution. Does that look uniform? It's skewed, isn't it? Someone said skewed. And which direction is it skewed in? Yeah, the p-values tend to be very close to 1, don't they? Now, I told you that the distribution of p-values should be uniform, so we should expect the same number of p-values to be between 0.8 and 1 as to be between 0 and 0.2. Yeah? But it doesn't look like that, does it? We've got lots of very high p-values, you know, and not very many low p-values. In fact, what this researcher did is they compared the kind of I don't know how they did it, sorry, but they said, well, look, we should expect a uniform distribution, but we've seen this distribution. How likely is it to get a distribution like this if the real distribution is uniform? And it was really small, you know, 3.8 times 10 to minus 100. Yeah? So then they challenged this Sato, this statistician, said to Sato, these p-values don't look right. They don't look like they've been, you know, all of the p-values are too high, you know, like looking like there's very little difference in baseline variables. You should have had more extreme. You should have lower p-values. And then he acknowledged he made them all up. So he'd made up 33 randomized trials. And so basically he sat in his office and he wrote down, you know, like when you're doing a trial, you know, you have your table 1, baseline variables. So he put some numbers in, you know, maybe he had a calculator. Anyway, they were all made up. And it was discovered because of this, using the baseline values. Baseline values are really important in detecting fraud. So, I'm surprised you don't know about this. I wonder if these get more, they're more known outside of the country than in the country. Maybe you're not particularly interested in, well, you're here, so you must be a little bit interested in misconduct. Because you're not interested. But anyway, so what we've talked about so far is the use of statistics to check the integrity of the data. But it's almost checking the integrity of the data after the trial is over. I mean, it's useful for people who are doing systematic reviews, but and the message is, look at the baseline variables. But the real value of using statistics, I think, is actually while the study is going. Now, I'm doing a trial at the moment called the CRASH 3 trial, and it's the same drug. We're very interested in this drug, tranexamic acid, you can tell. And now we're doing a trial to see if tranexamic acid can improve outcome in patients with head injuries. So basically, when you have a head injury, bam, you hit your head, you start bleeding inside your brain, and we wonder if you give tranexamic acid really early, can you stop this bleeding into the brain? So you get patients who, this is a patient who had a head injury, and this is a CT scan, a picture of his brain, and this is the bleeding into his brain he had when he came into the hospital, and then 24 hours later it's got much bigger. And so what we want to do is when the patient comes into hospital, give them tranexamic acid now and see if we can stop that turning into that. Yeah? So this is a trial that's ongoing. We've randomized 10,000 patients. We've got 3,000 patients to go. It's going all over the world. It's in the University of Tokyo. Tokyo Medical and Dental are recruiting. Senshu Hospital in Osaka. So quite a few hospitals in Japan, but lots of hospitals internationally. And we use statistics to check the integrity of the data. And so we look for unusual patterns in the data. We look for unusual data distributions. And we look for non-random data when you would expect to find randomness. Now, one of the things that we find in the trial is that we want patients to be recruited really early, really soon after their head injury, yeah? Because this bleeding starts really soon after if you fall off your bicycle or you get hit by a car, you start bleeding into your brain straight away. And if you're going to stop it, you have to actually intervene very quickly. But intervening very quickly is quite difficult, yeah? Because actually most patients, by the time you've found that there's a patient and you call an ambulance and the ambulance comes and they put the patient in the ambulance and they take the ambulance to hospital, and then the patient's got to get out of the ambulance into the emergency department, doctor comes along, finds out what's happened to the patient, and then gives the trial treatment. Yeah? It's very difficult to randomize people really quickly. And so usually we see that most hospitals, of all the patients in the trial, we get a distribution of time to treatment like this. Some hospitals, like about 10% of the patients are recruited in the first hour. 30% of patients are recruited in the second hour, and 60% of patients are recruited in the third hour. So it's very hard to recruit really quickly. It gets a little bit easier to recruit in the second hour. Now, we had one hospital that we thought, we had this distribution. Wow, that's really interesting. In that particular hospital, it seems that they can recruit lots of patients in the first hour, and actually they can recruit more patients in the first hour than they can recruit in the second and third, So that's the distribution for the whole trial, and that's the distribution in one hospital. Yeah? What do you think? Is it suspicious? Yeah? You're nodding over there. You think so? You think it doesn't look right? You'd expect there to be some reason. Okay. Well, this was a hospital in Pakistan. Yeah. And so what I did is I saw that and I thought like you, there must be some reason for this. Yeah?
But if I can't find any reasonable reason, I will suspect the fraud, protocol fraud,
Yeah.
or protocol violation.
Yeah. Okay, so when I saw this, I had the same impression as you. It's very strange. There must be some reason for it. And so I called the hospital in Pakistan and I spoke to the doctor. And the doctor said, yeah, it's my hospital is on a really busy road. In the middle of the town, there's a very busy road. It's a wide road, it's a big road, and the local boys have motorbikes, and they like doing what I don't know what wheelies. You know wheelies? You actually go woo like that, and the front wheel comes off the ground, and then you go along on the back wheel, and then you go down. Yeah. And he said the local boys like doing wheelies on the big road outside my hospital, and of course they fall off and hit their head, and so we get them really quickly. So that's what he said. Now, what do you think now? Is that a good enough reason?
I'm not sure.
Yeah.
Or I can't understand the situation, but why it relates to hourly transport?
Why it?
Why it relates to hourly recruitment?
Well, what he was saying is that the reason we can recruit so many patients within the first hour in this particular hospital is because the injuries happen just outside. Yeah, because if the hospital is here, there's a big road here, and the boys do this, bang their head, and then they're in the hospital. Yeah? What do you think? Is that who thinks that's a convincing explanation? You don't think so? Not really? Why not? Seems to be made up. So I thought it seemed to be made up. So I went on Google Maps. So I went on Google Maps. Now you can't see it very well, but this is Google Maps, and I looked at the hospital, and the hospital is there, and there's the main road. And actually, on this Google map, you can actually you can see the main road, you can see the hospital, and you can see little dots, and you think, well, maybe those are the boys doing the wheelies. Maybe this is true. Yeah, what do you think? Maybe this is true. There is a big main road outside his hospital. And maybe the boys are doing wheelies. Check the age? Yeah. Anyway, I was still suspicious. So I went there, right? So you get on an airplane, you go to Pakistan, you go a long way from London, and it's all hot, and and then you get in a car and you drive for 2 hours and you get to the hospital. Actually, no, you drive for 4 hours, you get to the hospital. There's a place called Narowal. Oh, I shouldn't say where it is. You forget that, please. I got to this place after a long drive, and I looked at the patient's notes. They weren't nothing to do with wheelies at all. These patients had come from all over the place. The data were they weren't accurate. What they'd recorded is the time from hospital arrival to receipt of the trial treatment. What we asked them to record is the time from the injury to receipt of the trial treatment. They were recording the time of arrival at hospital to receipt of the trial treatment. The data were wrong. So even though they gave you an explanation over the phone, the data were completely wrong. And we found at that hospital actually lots of the data were wrong. When they started off in the trial, they when they started off in the trial, they were putting lots of patients in, but we were monitoring the death rate, because the death is the outcome measure in the trial. We were monitoring the death rate, and the death rate was very low. So we're thinking they're putting lots of mild patients in because they're not dying. And so we said, look, we don't want you to put so many mild patients in, just put your severe patients in. We said, just put your patients with, I don't know if you're all familiar, but there's something called the Glasgow Coma Scale. You'll be familiar, but not everybody's familiar. Glasgow Coma Scale, it's a scale that measures the degree of unconsciousness. And we said, only put patients with a Glasgow Coma Scale of 8 or less into the trial. And when I was looking through the patient's notes, so you, basically after this 4-hour drive, you sit down in a hot room in this hospital and you start looking through the notes. And first of all, we noticed that all the times were wrong. They'd got that wrong. And then I started looking at the GCS, and I noticed the GCS is made up of different components. There are 3 components that give you this score. So you can get a score of 8 in many different ways. So I looked at GCS 8 made up of 332. GCS 8, 332. GCS 8, 332. GCS 8, 332. They were all GCS 8, 332. And I thought, oh, this isn't right. And then I actually got back to London, and actually because we did a very big trial in head injury a few years ago, we could see how likely it is that the 332 combination is a very rare combination, actually. You don't get 332 very often. So not only was there too many of these 332s, but actually the actual 332 combination is a very rare combination. Anyway, so then I got a very bad vibe from the investigator. He didn't ask me very much. He said he wanted a trip to London, and he wanted a new computer, which was a bad, you know, I was getting a very bad, anyway, we decided, there and then we said, right, okay, I don't think you're suited for this trial, and we're going to, we stopped recruitment then, and we haven't restarted. So we used, through the use of statistics, we found that the data from this particular center were unreliable. And usually we find that, there's something wrong, and usually it's a sort of innocent mistake, and we can put it right, and then we can start going again. In this particular case, we decided that it was too sloppy, you know, didn't understand, you know, we said, anyway, we closed that hospital down. Sometimes I go to places and I find very honest explanations. So for example, there was one hospital in Colombia that in one of our previous trials that we were seeing the data, and the data looked really strange. Patients who have a normal heart rate, but the respiratory rate is 0. Yeah? So the heart's beating, but they're not breathing. Now that's strange. Yeah? Do you agree? In your clinical practice, Tomoko? Never happens, right? Unless the monitor's off. Yeah, but so we had quite a few patients who had, they recorded the heart rate as 120 and the breathing rate as 0. So that means someone's heart's beating and not breathing. Usually if you stop breathing, your heart stops too. So it looked very strange. Anyway, we went there and to investigate, convinced that this was fraud, well, suspecting fraud, and we found out that it was an intensive care unit. All the patients were on ventilators. And so even though because the patient was on a ventilator, they decided that the patient wasn't breathing themselves. So they recorded their respiratory rate as 0. So it was just an honest mistake. So, anyway. And so usually we find it's just honest mistakes, and you can correct things. Looking at distributions of data is very helpful as well. And we look at the distributions of the data. We look at something called the coefficient of variation. Now, let me see what you think of this. So this is data from the CRASH 3 trial, and these are the blood pressures of the patients in the trial. Now, these are the site numbers. I know the identity of, but I don't want to share the identity of them all. Which site would you be worried about there? Are you worried about any site there? Do they look all right? No? Anybody? So D1, you're worried about D1 because the blood pressure is high. And you've...
L1, L2, and L3 are too similar.
L1, L2, and L3? Too similar. Okay. So we've got D1 because the blood pressure is high, L1, L2, and L3. Okay. Now I'm going to show you, I've shown you the mean. Now I'm going to show you the standard deviation. Yeah? The standard deviation of the blood pressures. Now, do you have any concerns about do you have the same concerns or different concerns? Who said something there? DN. Ah, right. So this is a new one now. So you've got DN. Why are you worried about DN?
I thought that's
Too low. So you're worried about DN because the variability is too low. So usually there's quite a big spread of data. The standard deviation is quite wide, but in this case it's quite narrow. Yeah. Anybody else worried about anything? Well, these are the p-values for these Levene test, right? The null hypothesis in a Levene test is that all the standard deviations are the same. And the p-value is that if the null hypothesis is true, that the standard deviations of all these variables are the same, how likely it is that we'll see a difference from the site one to the overall one by chance alone. And so the ones that come out are DN came out. It's a very low variability. Yeah, these data are not very variable, and it's a very statistically significant one. The L1, L2, and L3 they all also come out as having very low. So you spotted those because you thought these were so similar. And the variability is very low as well, so it's looking more like it. And the Levene's test is highly significant, and the coefficient of variation is on the low side. So we've identified which hospitals we want to have a closer look at. Yeah. So what we do is, you see, what happens with these big trials? We've got this trial. It's recruiting patients in, I don't know, 30 countries. It's recruiting patients from about 350 hospitals. Now we can't go to 350 hospitals in 20 countries because it's too expensive to do that. Yeah. So what we try and do is we try and focus our activities using statistics to tell us where we might have problems. And in this case, statistics identified L1 and L2 and L3 and DN, and we went to those hospitals, and there were problems there. In some cases, these L1, L2 and L3 are actually different units in the same hospital. And we found that they all came in through the same emergency department, and there weren't very many blood pressure measuring machines. So quite often the nurses, don't know how they did this, but they estimated blood pressure without measuring it. So you look at, like I would say, Callistus's blood pressure is 130 over 70, because he's awake and nice and pink, or he looks well perfused. So I haven't measured it, I've just estimated it. So we found that in this particular hospital, the nurses were kind of estimating is too kind a word, really. It's guessing. They were just guessing the blood pressure. And so what you see is they're always 120. Everybody says, what's the blood pressure? 120. Because that's considered the normal blood pressure. So if they look at you and you're talking and you look healthy, they say your blood pressure is 120. And there's very little variability. And so, blood pressure is not the most important variable in this trial. But that variable is a signal. It's a good test variable to find out if there's a problem, and you can look into it in more detail. So we use statistics to find problems, and we go and have a. The other one we use that a lot is something called the runs test. I don't know how many of you are familiar with the runs test. Nohiro, are you familiar with the runs test? Yeah? So the runs test is a really useful test. I'll just explain it. You get a series of values, right? They're separate values from different patients. So for example, say patients come into hospital. One patient comes in and they have a certain time to treatment. Another patient comes in, they have another time to treatment. There's no good reason to think that the time to treatment of that patient should influence the time to treatment of the next patient. They should be independent. Occasionally you might imagine something like, suppose there was a big bus crash and one huge ambulance went and got all the patients in and carried them to hospital at the same time. That doesn't happen very often, right? So you should expect the values to be independent. And so you get, these are just any numbers made up, but it's to show you what a run is. So here we've got 1, 2, 3, 4, 5, 6, 7, 8 numbers. We've got 8 numbers, and it happens to be the median is 41. Yeah? Now a run of values is a series of values that are less than or greater than the median. So this is one run. So 40, 30, and 10 are all less than 41. So that's one run. Then 79 is higher than 41. So that's one run. 20 is lower than 41. That's one run. 50, 47, and 42 are higher. Yeah? You got it? So there are runs. And so in this data set, there's in this piece of data, there's 4 runs. 1, 2, 3, 4. So 1 run, 2 run, 3 run, 4 runs. And that's what a run is. Now do you use this Stata? Do you use Stata here, or you use SAS or something else? What computer program do you use? You use them all, okay. So in Stata, there's a Stata command that you can do a runs test. And so in this data, there were 8 observations and there were 4 runs, and you can do this runs test, and there's no significant difference. In general, the number of runs is about half the number of observations. So you get the number of runs is half the number of observations. Now we've got, so we use this runs test for the time to treatment because we expect time to treatment, you know, this particular patient's time to treatment should be independent of the next one. And so I've got two bits of data now I want you to look at. And I want to tell you, so this one, can you count how many runs there are there? I mean, you can't, can you? It's very difficult. So, and then I've got another data set, this one. So you just read them like this. You go round this way, around this. So the median is 1.8, so that's one run to there, and that's another run, and that's another run to there. But it's not easy. It's not easy. So what I'm showing you is actually that sometimes you can look at data and see strange things, but sometimes you can't, and you need computers to help you. And so in this case, you know, there were 25 runs for site A, and when we look at site A results, we do a runs test, there are 54 observations, 25 runs. Or, you know, the number of runs is approximately half the number of observations. There was no significant autocorrelation. But in site B, there were 72 observations and 26 runs, so there were less runs than you'd expect. And this was evidence of autocorrelation. And in fact, because I could only get so much data on the slide, I didn't put all of the data, but the probability got really low. So we found an autocorrelation in this data, and you know, it was this particular hospital here, and it was time to treatment as well. Time to treatment, and the probability, the p-value for the runs test was very low. So we went to this particular hospital. And again, we found there was a problem with the data collection. They weren't, the data weren't being accurately recorded. In this case, what happened is the investigator realized that that they didn't have all of the information needed to calculate time to treatment. So she kind of estimated it. So she sat in her office basically and just thought, well, it'll be about this. It'll be about this. It'll be about this. And the thing about humans is we're not very good random number generators. Yeah? Humans are very bad at randomness. You know, we're not very good at making up random numbers. Generally, we underestimate chance, you know. The real data is much more varied than we make up. We have an idea of randomness, but we're very poor at generating random numbers. So the good thing about that is that if people are not recording data, real data, and they're actually estimating it or making up, you see less randomness in it than you really should do. And you tend to see less variability as well. And so those ways of detecting data. But so I've talked about statistics. This is Danielle, and she's the data manager on the CRASH 3 trial. And she found that data problem before the statistician did. So so good data managers are actually really important as well, you know. And so when you've got a data manager in your study, actually they're a really important part of your study. You want them to understand all of the study as much as possible, because they'll help you then. You know, they can spot things going on. So I've had data managers who've spotted all sorts of problems, like we had the first crash trial, we had questionnaire. There was a patient questionnaire at 6 months to ask the patient how they're getting on after their head injury. And we had one particular site, because the data managers organize the data and they see things that you wouldn't. So this, well, not this one, but the previous data manager, she noticed that all the questionnaires from a particular site were written in the same color ink. You know, they were written in this blue ink. And actually, when you get all of the sites and you get all of their questionnaires, because these are going out to patients, you know, some come back in black ink, some come back in pencil, some come back in red ink, but in this particular hospital, there was all blue ink. Yeah. So she spotted that, and it turned out that they were being filled out by the girlfriend of the investigator. So, you know, so we found out this, and we had to go send the questionnaires out again to the patients and get new data. And then this is another data manager in the crash trial, and she found something. Well, all of the patients in this trial have head injury, and we want to know the cause of death. We're very interested in the cause of death because the trial treatment will affect some causes of death but not others. So we ask the doctors at a particular site to tell us a little story about how the patient died. And what she noticed is that all the patients at a particular site had the same story. So this patient developed signs that, you know, his pharyngeal and tracheal reflexes became absent. He became pulseless and blood pressure shooted down to nil. He became pulseless and blood pressure shooted down. He became pulseless. It's all the same story. So what the doctor in this particular hospital had got, I don't know, lazy, yeah? And rather than write out the same story, rather than writing out the story in every particular case, cutting and pasting the same story. And statistics couldn't have spotted this one. You know, you can't get statistics to, you know, I mean, you maybe some clever machine learning or something, but a clever human can spot things like this. So you want to have the best use of statistics and clever humans as well, and they can help you. So to finish off then, usually statisticians are involved at the start of a study and at the end of a study, and in the middle they're not involved at all. I'm saying that if you want to improve the quality of the data, statistics can be involved in the middle. And it's much better because it's prevention. Yeah? You don't want to find out about poor quality data at the end when you can't do anything about it. You want to find out about poor quality at the time it's happening so you can improve it. Yeah? So statistical methods can and should be used to improve data quality. Statistical methods is not a substitute for good data management, and so you shouldn't try and say it's all the machines can take care of it. We don't need clever humans. You do need clever humans. Preventing data problems is better than detecting them. And you focus on the data collection system rather than allocating blame. Now that's been a really difficult one for me because you feel basically I do these big trials, and you spend about 8 years of your life working on one trial, yeah, and you can only do so many trials and then you die, because you don't live forever. So you put a big part of your life into these studies, and you find these investigators who are not taking it seriously, and you get, it makes me angry, you know? And I want to tie them to the chair and how dare you? That's my impulse, is to do that, yeah? But it's the wrong impulse. So fortunately I work with other people who are more sensible than me. And if there's a problem with data quality, they say it's a system failure, right? So when we had the doctor in this particular site in Pakistan, who was making up all the same GCS, 332, 332, 332, time to treatment was all wrong. What we've got to think about is how we select investigators. Are we selecting the right investigators for this study? Are we selecting the right investigators? Do we give them feedback early enough? That's one thing, a big thing that's changed, because so for example, if I show you this really strange looking data, there was 308 patients here. 308, 106, 100. So actually 400 patients had been recruited before we started to see statistical evidence of a problem. It's a bit too late, isn't it? The thing about statistics is that actually you need some numbers. So what we're starting to improve our data collection systems by actually, let somebody recruit the first 10 patients and then review the notes of those 10 patients, right? Audit the data you collect from the first 10 patients. So what we do is we do it by Skype usually. Because we don't want to keep on, flying around the world. So we do it by Skype, and we get we say, right. And the good thing about Skype is you can just hold the notes up to the camera. You say, show me this patient's blood pressure. You say, there it is in the notes. And show me how did you work out the time to treatment? You say, well, we worked out from when the ambulance was called. Show me the time that says the ambulance is called. And so we try and tackle problems really much earlier. And so so actually moving away from a culture of blame and thinking of data quality as a system feature is much more useful. And that's what we're going to talk about tomorrow. Tomorrow we're going to talk about a very a very high profile, another Japanese case of research misconduct, a very famous, I don't know if it's famous in Japan, but it's very well known out of Japan. I'm only doing that, I don't think misconduct is no more common in Japan than anywhere else. I don't think there's any evidence that that's the case. So I've chosen examples because I'm in Japan. Yeah. If I was giving this course in Korea or Nigeria, I would choose examples from those places. So tomorrow we'll look at a high-profile case of misconduct and look about how the university and different groups have responded. And I want to consider the issue about whether we consider misconduct as a individual failing, a rotten apple, or a system failing, a rotten barrel. Yeah. So, any questions about what we've talked about so far?
Professor,
Yeah.
today you are talking about the statistical methods for checking the data integrity, but all of your example is like a clinical trial. I just wondering, are these statistical methods
can also enroll in the other field like public health.
Hmm.
Yeah.
So, like, some of it can and some of it can't. So, the good thing about clinical trial is that you're comparing two groups that should only differ by chance alone. So all the stuff related to baseline variables, that only applies in clinical trials. It wouldn't apply in a cohort study, yeah? So if you have a cohort study, you know that you don't expect them to be different, yeah, at baseline. So you might say, let's look at if smoking causes lung cancer. You take a group of smokers, a group of non-smokers. Now, they're going to be different from many things apart from the smoking, aren't they? So randomized trials give you this special opportunity because randomization gives you two groups that should differ only by chance. But all of the other things about data distributions, yeah? So if you were doing, what sort of study are you doing?
We just go to field and to collect the data by questionnaire. It's like very normal way in public health.
Yeah.
Yes. So
Okay. Okay, so say you were doing a questionnaire survey and you had lots of hospitals, yeah? Or lots of, you might have different villages collecting data, right? So you might look at the overall distribution of the variables, say it could be like age or the average family size or something like that, and look at that by village. And you might look at the distribution of the data, look at the average family size and the distribution, and you might find that in one particular village, the variability of family size is very small. And you might find that, and I was talking to, this happened in the London School of Hygiene. There was a study in Africa where related to HIV, and they found that one of the data collection sites, the data had very low variability. And they investigated, and in that particular site, rather than going to the trouble of distributing the questionnaires and collecting the data, the researcher in that particular site had filled in the questionnaires.
Thank you.
Yeah. So you can use some of them, but not all of them. More questions?
Thank you. I'm just curious about operation detail. You mentioned the nurses get the blood pressure by evaluate. So I mean, how when you go to the hospital, how to observe the results? You play as a patient.
No, we just go and no, we don't pretend we're a patient. No, They wheel me in on the trolley, and I'm looking, pretending to be unconscious. No, I just go in and we go to the hospital. I go and sit in the emergency department. About 3 weeks ago, I was back in Pakistan, and I spent a couple of days in the emergency department and just watching how the patients get recruited. And
They don't know who you are.
oh yeah, they know who I am. Yeah, they know I'm from London and I'm from the trial, but you still find out an awful lot. Yeah, you just see how things are done, and people usually just tell you, this machine doesn't work, so I estimate. It's usually. I think it's the most useful thing that I do. Actually, is see how it really works. Right? When you do these trials, or when you do any research, you've really got to get into it, you know, and really see how it works. So what sort of studies are you doing? You know, because what you can do is you can sit in the university and, you know, send out instructions to the world, you know, and then receive back news from the world, and then do your p-values, and it doesn't work that way. You've actually got to go and you've really got to investigate, you know, get into the, and then you know, it really helps you make better studies, because some of the times you know you're doing things. Sometimes you have expectations that are really impossible, you know, and so if you see what it's really like, I mean, always with me when I go, I realize I have to simplify things. Things being too complicated is a real problem, because usually the people who are doing the data, if you're getting doctors to collect data, collecting data isn't their main job. You know, they've got more important things to do than your study usually. So if you want them to do it well, you have to actually minimize, you know, cut a lot of things out. Yeah. Do you get the opportunity to go to sites? Have you been to?
Yes.
Yeah. Where are your sites?
Taiwan.
In Taiwan.
In Taiwan, yeah.
So are you from Taiwan?
Yes.
So you go there and you.
Yes, I last year it's my qualitative study, and this is quantitative study.
Yeah.
So I just finished the pre-test my questionnaire.
Yeah.
And I entered the reliability now, and to revise the questionnaire.
Yeah.
Again.
And then when you give it, who's going to administer it?
I just went to the school, the high school, and to distribute my questionnaire.
You distribute your questionnaire in the high school.
In the high school, yeah.
Okay.
Yes.
And you, so you distribute it and you collect it in.
Collect it in, and 1 week later I just collect again, because I want to do the test retest reliability.
Okay.
Yes.
All right.
Yeah.
And that's good, because if you're in the actual classroom, you can find out what's going on. I mean, it could easily be that because you know sometimes they give it to the teacher, don't they?
Yeah.
You give the questionnaires for the teacher. You don't know what the teacher's going to say to the children, do you? You know.
So
What's the answer to this one? It sounds.
Yeah. So the best way you just go to.
You have to be there to
Yes.
see what's happening. Yeah. Anybody else have experience going to site and actually seeing how things work and being surprised or not surprised? Yeah? Tell us about your experience. Is this in Kenya?
Yes, I actually came back like 3 days ago.
Ah, okay.
So I took, mine was in the household, in the community. So
Mm.
I go with the research assistant, and I need like 25 people from each village. So if I go with 4 assistants, I'm the 5th one. So we collect each five questionnaires per day. We collect data from 5 people, each person. So I have to go with them, and sometimes I get like discouraged if some people decline, or because we have to go to each household and then book them for the test for the next day. Like I was collecting data on diabetes and hypertension, so we have to do the test in the morning before they take breakfast. There are a lot of things you have to adjust. Some people don't turn up, some people come when they have already had their breakfast, so you have to book them again. Some people, they wanted to do the questionnaire, but they don't want the test anymore. So yeah, there are many experiences.
It's very interesting, isn't it? Because I think when you actually get involved like that, you start to see the study from the perspective of the data collectors.
Sometimes they get very tired, like we have to get to the field by 6 a.m. And because then after 8, people have had breakfast. So waking them very early, like 4 or 5 a.m. So I have to give them time the whole afternoon to sleep for the next day.
So this breakfast thing is very... breakfast. Is breakfast a dichotomous variable? That's the question. So what constitutes breakfast? Yeah?
In the village where we were doing the collection, the people wake up very early. So we tell them not to eat anything.
Yeah.
So some people will say, I haven't eaten anything, but I drank some tea.
Yeah.
So it's already...
Well, I'm one of those. Whenever I go for... I'm a coffee addict, yeah? Coffee is my... I don't drink alcohol or anything, but I love coffee. And as soon as I wake up in the morning, I have to have a cup of coffee really quickly. I just want a cup of coffee immediately. And so whenever I have to go for my cholesterol test and they say, don't drink anything, I just lie. I have a cup of coffee always. I might not put milk in it, but I don't think there's much cholesterol in coffee, is there? But anyway, the doctor says, have you had anything? No. But I've had my cup of coffee. So anyway, any more experiences that people want to share? No?
I have a question.
Yes, please.
Not the experience. I'm sure you thought there was a central management of data, but how about local management system? Usually, we will put the local monitoring in each facility.
Uh-huh.
So, but today's topic was mainly central. So my question is, what kind of tasks can local management system do?
Local monitoring.
Yeah.
Yeah, it's all about cost effectiveness, isn't it, really? Because I think it's a question of cost effectiveness. If you could, so it's a very interesting question, I think. See, on the one hand, you could check every single variable, couldn't you? You're doing a study, and you could check every single variable. So somebody collects data, and then you have somebody else to go and collect it again, and you check every single variable. Now the thing is, that would reduce the measurement error, that would reduce the error, but it'd be quite expensive, wouldn't it? Now the thing is, there are two kinds of error in studies. There's probably more kinds of error, but essentially there is measurement error and random error. Yeah? Now, if you put a lot of your money into reducing measurement error, the study will be smaller because you've spent all your money on reducing measurement error. Usually you've got a fixed budget, haven't you? So if you put a lot of effort into reducing measurement error, random error will go up. And so you're always dealing with this balance, right, of measurement error and random error. So in our studies, what we find is that the reason why we like statistical monitoring is because it's very cost effective. We can have lots of centers all around the world, and most people do everything okay. Lots of centers, lots of data collection, really reduce random error. And then we want to be as cost effective as possible for reducing measurement error. So we do statistical data checking and only go to those places. So I think your question is a very good one. But I think it's about cost effectiveness. And what people don't realize is you're always making a trade-off between the size of the study and data checking. You can check lots of data, but the study will be smaller. If you do less checking, the study can be bigger. So it's getting the right balance between data checking and size of the study. I prefer big studies with minimum data checking, actually, because what I found is that, especially where you get a variable, where you get a primary outcome that's really clear, like death. So in our studies, you know, I don't think I've ever found errors in the recording of death, you know, that said the patient's dead when they're actually alive, or the patient's alive when they're actually dead. You know, it's always recorded really well, that. And so actually, because primary endpoint is death, you just go for big numbers. Yeah. It was a good question, that one. Owarimashita. Have we? Okay, well, I look forward to seeing you tomorrow. And tomorrow we're going to talk about responsibilities and things like that, rotten apples, rotten barrels. On Monday, we're supposed to have 2 sessions, but I'm not sure. Maybe on Monday there was going to be a meeting in the morning and then one in the afternoon. Is the afternoon convenient? I was thinking we might not. Yeah? In the morning, what I want to do is I want to give you some scenarios, right? Maybe we'll do some more role play. I thought you were very good as the editor of The Lancet. And you're a good lawyer too. So I like doing this role play because one, it's fun, and the other thing, it's sort of I don't know, you start to feel what you might do, you know. So I want to do some role playing of what you might do if somebody encouraged you to change data, or you noticed the data had been fabricated or falsified. Who would you tell? Those sorts of things, yeah. So I'm going to, on Monday, I think maybe we'll get some of these, move some of these tables back, and we'll put the chairs in a circle, and we'll have some.
I think it's going to be in another room.
Oh, it's going to be in another room?
Building G.
Okay. Well, we'll try and get some, we'll do some role play, but do come for that, because I want some good acting, and I think that can really help, because it's, you know, sort of what you would really do in that situation. It's quite difficult. It's a very difficult area. Okay, good. And there'll be a certificate at the end. Shomeisho. So you have to come on Monday, otherwise you don't get a certificate. And then don't forget, if you get a chance to read about this story about in the news or on the internet about the Tokyo thing,